So hopefully what we've learned so far in thermodynamics is that thermodynamics is awesome, right? And if you don't believe me yet, well, I'm going to keep trying to convince you, right? So keep walking the path with me, and hopefully you'll get to the point where you realize that really understanding thermodynamics helps us understand the universe, but more importantly, as engineers, it helps us make really practical machines better, even if we don't have a perfect understanding of how they're working in the real world. So we've been talking about heat engines, and in particular, we're interested in nuclear and coal-fired power plants that run on Rankine cycles. Now we know that to characterize the thermal efficiency of heat engines, we need to know the energy benefit divided by the energy cost. And in these kind of engines, the energy benefit is net power, and the energy cost is that we have to add heat to the system, maybe by burning coal or maybe by running a nuclear reaction. We also know that if we know the temperature of our hot reservoir and the temperature of our cold reservoir, that's where we're adding heat and where we're rejecting heat to, then we can define the Carnot efficiency. Now, I've been telling you that these Rankine cycles are important because they make up almost half of the energy that we put out onto the grid here in the United States of America, right? And we talked about sort of the most basic Rankine cycle that we can have needs to have at least these 4 components, and that the purpose here is to generate power. So what we really want to do is we're running through the turbine, and then we do all this other stuff just to get back to the turbine inlet. We did an example problem before about this 4-component Rankine cycle, and we saw that we got an efficiency of just under 30%. Now we know that we can't compare the performance here to 100% efficiency because that's just impossible. So the impossible performance that we want to compare to is the Carnot efficiency, which even though it's not possible, at least we could asymptotically approach. And I think in this case, the Carnot efficiency was kind of in the mid-50s. So we have some room to improve here. So how do we improve efficiency? I guess before even we talk about how, we need to say why it's important to improve efficiency. So when we're running these power plants, if we get better performance, higher efficiency, we save money, right? But maybe even more important than that, we reduce emissions because we can get the same power for less heat, or if we're putting the same heat in, we get even more power out. So we want these processes to be Lorax approved. So how can we improve the efficiency of these cycles? One of the ways we talked about was by making the cycle more complicated. That 4-component Rankine cycle is kind of like playing with Duplo, which is good because it helps us to understand how things work, but really, if we want to get into something that looks like a real power plant, we want to maximize the efficiency, and part of the way we do that is by increasing the complexity of the cycle. Now, the first mechanism, or the first, I guess, strategy we've talked about for doing this is to add 2 turbines. So here we have a high pressure turbine where we go from the high pressure at the first turbine inlet to some intermediate pressure that's between the turbine inlet and the condenser pressure. And then in between these 2 turbines, we run our working fluid back through this boiler so that we increase the enthalpy of the fluid again before running through the low pressure turbine. I made the argument last class that doing this improves our thermal efficiency, that basically, even though we're increasing our turbine power, so we're increasing our net power here because the pump power stays the same, and we're getting more power out of the turbines, but we're also increasing the heat that goes in, right? So I made the argument last class that when we do this, what happens is we're increasing the net power faster than we're increasing the heat in. Now, maybe you'll just take me at my word, because this does kind of make sense, because here we're adding some more heat, but we're doing that to make some steam some higher temperature, right? So it does kind of make sense that it's easier to increase the temperature of steam than to boil liquid water. But, like all good scientists and engineers, it's important to be skeptical. So I'm going to show you in the example that we do today that doing this reheat cycle does improve thermal efficiency, at least in the case that we look at today. And I know, so on Mythbusters, they might tell you a test of 1 is the same thing as a test of none, and that's good advice to live by, but a test of 1 is still better than nothing, right? So we're going to show it one time here, but then we'll do it more and more as we go through the class, and you can see that this is a viable strategy. This is something that we actually use to improve efficiency of Rankine cycles. So we talked about the Rankine cycle, and the thermal efficiency is still going to be net power divided by heat in. But unlike the 4-component cycle, there's more terms to deal with here, right? So our net power, there are 3 pieces of equipment here that power is important for. The first is the high pressure turbine, which is going to produce power. This is work out. Work out is positive. We have the low pressure turbine, which is also going to produce power, right? So both of these things are benefits. They're increasing our power. But the pump over here is consuming power. So I'm going to do the first law on all these 3 components, adding them all together, recognizing that the turbine powers are positive and the pump power should be negative if I use the first law. The other thing, and this is the one that usually for me, if I'm going to mess up, I'll forget that I'm adding heat in 2 places here. So I add heat as I move from state 6 to state 1. That's when I'm boiling fluid. I start with a liquid and I move it to a vapor. But then I'm also reheating here, taking what comes out of my turbine. In this case, it looks like that's a superheated vapor. And I'm increasing it back to this other superheated vapor state. So I add heat 2 times, and I got to remember in the reheat cycle, right? That means you heat it and then you heat it again. So I got to remember to add both of those heat transfer terms in the denominator. How do I find those terms? Well, I'm glad you asked. I do a first law analysis on each one of those components. And typically, I'll make this list of assumptions, where all the components typically would be steady state, 1 inlet, 1 outlet, no change in kinetic energy, no change in potential energy, and then each component would be either adiabatic, typically turbines and pumps, or passive, those are the ones with no fan blades on the inside, like you'd see in a condenser or in a boiler. And then also, I'll typically, in between states, I'll assume that there's no friction losses and no heat losses, so I don't have to separately calculate the state at the outlet of the turbine and then again at the inlet to the condenser. After I do that, I'll get equations that look like this. If I'm talking about turbines and pumps, I'll have mass flow rates times H in minus H out. And if I'm trying to find a heat transfer rate, I'll have the mass flow rate times H out minus H in. After I get to this symbolic part of my solution, I have to ask myself, well, what's the fluid? And in this case, if you're talking about a Rankine cycle, the fluid is going to be water or something like water, where we're moving back and forth across the vapor dome. And when I find delta H, usually I'll have to say, what's the phase? So my turbines, I might have the inlets and outlets as superheated vapor. But with my pump, I have subcooled liquid on both sides of the pump. So if I'm talking about an ideal pump, I can use that special equation, the specific volume, multiplied by the change in pressure. Again, here from the first law, I'm going to assume that, well, it's more than just an assumption. I'm going to find that turbine powers should be positive, pump powers should be negative, boiler heat transfer rates should be positive, and condenser heat transfer rates should be negative. So today, what we're going to do in this lecture is do an example where we solve a reheat Rankine cycle. So on a problem like this, I might get a semi-complete state table that looks something like this, where the problem has already solved state 1 for me, and state 3 for me, and state 5 for me. I know something about state 6S, but I don't really know anything about state 6. I'm told, though, that as I move through the turbines, I have an 85% isentropic efficiency. Now, the problem is asking me to find the thermal efficiency. So, what is the thermal efficiency for a Rankine cycle? I know Rankine cycle is a heat engine. The energy benefit is the net power, and the energy cost is the heat transfer rate in. So, in this case, to find my net power, I look for the components where power is what's going to be left when I do the first law. And there are 3 components there: a high pressure turbine, a low pressure turbine, and a pump. So I'm going to add together the power from all 3 of these terms. I'm going to use the first law to find the power for all 3 of these terms. And I'm going to recognize that the turbine powers will be positive and the pump powers will be negative. Then I'm going to think, okay, where am I adding heat? And I'm adding heat in 2 places. So the first is as I move from state 6 to state 1. I'm going to call that Q dot in the boiler 1. So Q dot sub B1. And the second time when I do the reheat. So that's Q dot B2. So now I got an expression for the thermal efficiency. Unfortunately, I don't know any of these terms. I don't have the turbine power. I don't have the turbine power in the low pressure turbine. I don't have the pump power. I don't have the first time that I'm adding heat. And I don't have the heat transfer rate when I do the reheat. That tells me that I've got some work to do with the first law. So for all of these components, I'm going to use the first law. I'm going to say that we're at steady state, that we have one inlet, one outlet in all of these components, that there's no change in kinetic energy, no change in potential energy, and that the pumps and the turbines are all adiabatic, and the boilers, where we're adding heat, are all passive. I'm going to say that there's no friction losses, and that there's no heat losses in between the lines. So, these are the equations I'm going to get. For the high pressure turbine, I'll get the mass flow rate through the first turbine times H1 minus H2, H in minus H out. For the low pressure turbine, it's still m dot times H in minus H out, but H in is H3 and H4 is H out. For the pump, again, still m dot times high ho, but now I'm expecting a negative number. So this is the mass flow rate through the pump times H5 minus H6. Through the boiler, now I'm talking about heat transfer, so Q dot is going to be m dot times H out minus H in, or the mass flow rate through the first leg in the boiler times H3 minus H2. The reheat part of the cycle is going to be the mass flow rate through the second part of the boiler times H1 minus H4. I'm expecting everything here to be positive except the pump power, which I think will be negative because this should be work into the system. So now I got all these different mass flow rate terms, right? So really, I can do conservation of mass on all of these components. And when I do that, I'll assume that each component is at steady state and that each component has one inlet and one outlet. That means for each component, the inlet mass flow rate is going to be the outlet mass flow rate. But all of these components are lined up in series and we don't split the mass anywhere in the system. So that means that the mass flow rate through the turbine is the same as the mass flow rate through the second turbine, which is the same as the mass flow rate through the condenser, and so on and so on. There's only one mass flow rate in this problem. So I'm going to change all of these mass flow rates to just m dot. I can lose the subscripts because they're all the same mass flow rate. Now I can put in my expression for all the powers and all the heat transfer rates into my thermal efficiency. So I found W.T1, W.T2, W.P, and the heat transfer rate terms. So now I'm going to put these in. I've color-coded them to remind myself which ones are going to be positive and which ones are going to be negative. I see that I can factor out the mass flow rate from the numerator and the denominator. So all these mass flow rates are going to cancel out. And I'm left with the thermal efficiency that's H1 minus H2 plus H3 minus H4 plus H5 minus H6 divided by H1 minus H6 plus H3 minus H2. So this is great. I'm at a really good position here because I've demonstrated to everyone that I know how to use the first law of thermodynamics on a series of different components to get to a symbolic solution for thermal efficiency, right? And it doesn't matter how complicated my cycle is, I'm always going to use these skills to find this type of symbolic equation. But now I got to go through the effort of filling out all my state table, to find these specific enthalpies. Thankfully, the problem told me some of these things. So I know H1, I don't know H2, I do know H3, I don't know H4, I do know H5, I don't know H6, I do know H1, I do know H6, I do know H3, and I don't know H2. So if I did know H2, 4, and 6, then I could get a numerical answer for the thermal efficiency. So how do we go about doing this? So I see that I don't have enough information to fix state 2, right? Because the only thing I know about state 2 is that the pressure is 10 bar. I can't fix state 4 where I only know the temperature. And I can't fix state 6 because here I only know the pressure. So instead, I've got to use the information that they tell me about these processes, which are that all the isentropic efficiencies in this problem are 85%. So the isentropic efficiency of both turbines are 85%, and the pump is 85%. So now, and I guess I knew this by looking at the state table anyway, I have to find first the isentropic outlets of the turbines and the pump, and then I can use the isentropic efficiencies to find the real outlets for the turbines and the pumps. So let's go about doing this. So first I got to remember that the isentropic efficiency for a turbine is going to be the real power divided by the ideal power, because remember the turbine power is a benefit. So the second law, or the irreversibilities in the universe, work to reduce the power in the real case, so the real power is less than the ideal power. So here, my equation for the isentropic efficiency is going to be H in to my real turbine minus H out of my real turbine divided by H in to my real turbine minus H out of the isentropic or ideal turbine. So if I wanted to find the real outlet state of my turbine, that's going to be, if I rearrange this equation, H in minus the isentropic efficiency of the turbine multiplied by H in minus H out of the isentropic turbine. So what I need to do is find the isentropic outlets for both turbines before I can find the real outlets. So let's look at state 2s. Here I know that the pressure is 10 bar. Because this is an isentropic turbine, I also know that the specific entropy at the exit of this first turbine is the same as the specific entropy at the inlet of the first turbine. So that's 6.8778 kilojoules per kilogram Kelvin. So now I got to use my tables. I got to figure out if this state is a two-phase mixture or if it's a superheated vapor. So the first thing that I would do, I know that my pressure is 10 bar. So here I can look at the superheated vapor tables and I find the one for 10 bar. And then I'm going to look here. This is the saturated vapor case. So in the saturated vapor case, the specific entropy is 6.5865. This is SG if I looked on the two-phase tables. So now my S of 2S is bigger than this SG. So that means at this pressure, I must be a superheated vapor. So now I look, where am I on the table? And my actual specific entropy here is in between the specific entropies at 200 and 240 degrees. So now I need to interpolate. I can find my interpolation factor using the actual outlet and then the values off the table. So when I do this linear interpolation, I find that I'm really, really close to being at 240 degrees. I can now interpolate for H because I don't actually want to know what the isentropic efficiency is. I want to know what the specific enthalpy at this isentropic outlet is. So I can take this equation for linear interpolation and find that the specific entropy in this case is 2,919.7 kilojoules per kilogram. So I can put that onto my state table. So now that that process is fresh in our minds, let's do the same thing for the isentropic outlet of the second or low pressure turbine. right? So here I know the temperature, but I also know the specific entropy is 7.3011 because that was the specific entropy at the inlet of this second turbine. So now I'm going to look on my two-phase table. I see that S of 2S is 7.3. Is that in between SF and SG at my temperature of 95 degrees? And it turns out that it is. So I have some quality here that's going to be between 0 and 100, right? Or between 0 and 1. So now I can do some interpolation with quality here. So I can find that the quality at state 4S is 0.98. So again, I'm very close to being a saturated vapor here, right? So this is 0.98. And then I use my equation for quality to find the specific enthalpy at this isentropic outlet. And in this case, that's 2,625.9. I look at this and I see this is pretty close to Hg. So that feels pretty good, right? I have reasonable confidence that this answer is correct. So I put this into my state table as well. So now that I know the isentropic outlets, how do I find the real outlets? Right? Remember, I had this equation for isentropic efficiency. And from that, I can find the real outlets from this turbine if I'm given the isentropic efficiencies. So in this case, for both the high pressure and the low pressure turbine, I don't know H out in the real case, but I do know H in. I know the isentropic efficiency, and I know H out in the isentropic case. So I can find that H2 is just about 3,010 kilojoules per kilogram, and H4 is 2,705.7 kilojoules per kilogram. So now I've found the real outlets from both turbines. So that's pretty good. There were 3 specific enthalpies I wanted to find, but now I know 2 of them. So how do I go about finding the pump's real outlet? So now I want to think about the isentropic efficiency for a pump. Isentropic efficiency for a pump is again power over power, but because the power consumed here is a cost to the cycle, then we have to pay more in the real case than we would in the ideal case. So we put the real power on the bottom, and we can see that the isentropic efficiency is H in minus the isentropic outlet divided by H in minus the real outlet. What I want to find is H out, so I can rearrange this a little bit, do some arithmetic, and find that H out, the real outlet of the pump, would be H in minus H at the isentropic outlet divided by the isentropic efficiency. So remember, this equation is a little different than with the turbines because in this case, the fraction here, the ratio, is flipped over with ideal on the top and real on the bottom. In this case, we didn't have to use the ideal pump equation. We were just given H6S. And if we were given H6S, then we can use it to find the real outlet enthalpy. So now I put this into my state table as well, and I see that now I know the specific enthalpy at the outlet of all the turbines and at the outlet of the pump. So now I should be able to find my thermal efficiency because I know all the enthalpies in this equation. So now here I've seen that my delta H across the first turbine is positive. My delta H across the second turbine is positive. H in minus H out across the pump is negative. That's what I'm expecting. And the delta H's that correspond to the heat transfer rate in both cases is also positive. So in this case, I can find my thermal efficiency for this reheat cycle as 29.2%. So here, what we did was we increased the complexity of the cycle by doing this reheat analysis. We kept the turbine efficiencies and the pump efficiencies the same, and we see that we get an increase in the thermal efficiency. So this means we're getting more work out for the same amount of heat that we put into the system. So this does increase our thermal efficiency. We've still got room to go, so we can continue to increase the complexity of the system to improve the thermal efficiency, but we're on the right path. And if you go to a real Rankine cycle, there's going to be all kinds of different things that people are doing to increase the thermal efficiency. And we'll learn about another method for increasing Rankine cycle efficiencies in our next class. So thanks for joining me here on Thermodynamics. I'll see you again next time.